So we're going to start a new module, and this module just kind of starts us off with rational expressions and rational functions. So a rational function really is not new to us, just we're going to take it one step further. This is where typically you have a variable in the denominator. So more specifically, though, a rational function is going to have a polynomial in the numerator and a polynomial in the denominator. So that is our definition of a rational function. So if we're trying to evaluate our rational functions, all that means is that if you're given a value for x, you need to find the corresponding value for y. Okay, well, recall that f of x is the same as y. F of x is just what we call function notation. And so for problem number 1, what this is asking is it's saying, hey, if x equals -1, what is y? That's all it's asking. And so to find f of -1, we go ahead and substitute -1 for x everywhere we see it in our problem or in our function. And so then we simplify this. So that's going to be 2 over a -5. Okay, so to answer the question, f of -1 is equal to a -2/5. So it doesn't matter if the negative is in the denominator. That negative is assigned to the entire fraction. So it can be in the denominator, it can be out front, or it can be in the numerator. They all mean the same thing. Now let's go ahead and look at the second problem, f of 0. And so for f of 0, we're going to substitute a 0 everywhere we see that x. And so that's going to give us 3 over -4. So f of 0 is equal to -3/4. For the last one, f of 4, that problem is saying substitute a 4 everywhere where you see an x. So that's going to give us 7 over 0. We recall that you cannot have a 0 in the denominator of a fraction. And so we would say this is undefined. And so you can recall that when we were looking at domains for anytime we had a basic function with the variable in the denominator, we were most concerned that that denominator, the x, would only include numbers in which it would not create a 0 in the denominator. So, or a simpler way of saying that is any numbers that create a 0 in the denominator are excluded from the domain. So in this case, our domain would not have a 4 in it because it would create a situation in which our function is undefined. All right, so that leads us to the next thing, which is how do you find the domain of a rational function? So remember that the domain are simply the x values. That's all we're concerned with at this moment. So the first step is to set the denominator equal to 0. Does it say anything about the numerator? No. Okay, we're only concerned about setting the denominator equal to 0 to find the domain. then the domain is the set of all real numbers, excluding any values we find in step 1. Okay? All right. So let's go ahead and find the domain for this g function. So we've got g of x is equal to x plus 2 over x squared plus x minus 42. So the very first thing that I want us to do is ignore x plus 2 in the numerator. It has nothing to do. Okay, the numerator does not impact the domain or the x values. Okay, so we're going to go ahead and take this denominator and set it equal to 0. And so then we factor that, that trinomial and get x minus 7, x plus 6 equals 0. We use the zero product rule to find that x is equal to 7 and x is equal to negative 6. So these are the excluded values. Okay? Or in other words, they are not part of the domain because they're going to create a 0 in the denominator, and that makes it undefined. So to show this in set builder notation, it would be the domain. Okay, so in set builder notation, the domain is going to be the set of real numbers, but x cannot be equal to negative 6 and x cannot be equal to 7. If you want to show the exact same thing in interval notation, I think it's easiest to first graph it, and that's what this graph shows. Then from that graph, you can identify each of the intervals. So that's where we get parenthesis, negative infinity to negative 6. Then you use your union symbol, start up with negative 6 again, I'll go all the way to positive 7, union, positive 7 to infinity. Okay? All right, so let's go ahead and find the domain of the following functions. So step number 1 is going to be to find our excluded values. Okay, and so that's going to be x squared minus 4 equals 0. Now, we just finished the whole factoring thing, that whole factoring module. And so one of the things that I hope you remember is that this is the difference of two squares. And so we can go ahead and write this as our conjugates, x minus 2, x plus 2. Set each of those factors equal to 0. So x minus 2 equals 0, x plus 2 equals 0, x equals 2, x equals negative 2. They are excluded from the domain. Means x cannot be 2, cannot be negative 2. So let's go ahead and put negative 2 and 2, and we'll put open circles there and shade everything outside of those open circles. So now we can easily find our intervals. So we're going to go from negative infinity to negative 2, union, negative 2 to positive 2, union, 2 to positive infinity. In set builder notation, then our domain, and I should write that, that's our domain. Our domain is squiggly bracket, the set of all x such that x is a real number and x cannot be equal to -2, and it cannot be equal to +2. There we go. All right, let's go ahead and do, we've got 2 5s here. Let's do the number 5 that's to the right. All right, so the first thing we want to do is we want to factor x squared minus x minus 12. So we set that equal to 0. So I'm looking for what can I multiply that gives me -12, but then adds to a -1. Well, I'm thinking 3 and 4, and if I make 4 negative. So that's going to be 3, I'm sorry, where's my head? It's going to be x plus 3, x minus 4 is equal to 0. So then I set each of those factors equal to 0 and solve. So I get x is equal to -3, x is equal to 4. Those are my excluded values. Here's what we're not doing at this point. We are not finding x-intercepts. We are just focusing on the domain for these rational functions. So the domain again is the x values that are allowed to be used as inputs to this function. Okay, so if I put -3 and 4 on the number line, shade in around those, it helps me identify my intervals. So my domain is going to be -∞ to -3, union -3 to 4, union 4 to +∞. Now I can do my domain in set builder notation. So it's the same thing. It's just a different method of stating the domain, set builder notation, but we want you to know how to do both. So this is going to be squiggly brackets, the set of all x such that x is a real number, okay? But x cannot be equal to -3, x cannot be equal to +4. There we go. All right, let's go ahead and do this next problem. Again, we are only focused on the denominator. We have not talked about the numerator at all. It has nothing to do with finding our domain. So I'm going to take my x squared plus 3 and set it equal to 0. Well, that's going to give me x squared equals -3. So what number can I input in for x that's going to give me a -3? And the answer is none. Nothing, or no, I should say no number can be squared to equal -3. Because if you take 2 positive numbers, that'll give you a positive. 2 negative numbers multiplied will give you a positive also. So that means there are no exclusions. So my domain is all real numbers. -∞ to +∞. That's my domain. In set builder notation, that'd be squiggly bracket, the set of all x such that x is a real number. Okay, let's look at problem 6. So problem 6, we're going to do the same thing. We're going to take that denominator and we're going to set it equal to 0. So this one is different than the problem we just finished. This one, we've got a minus sign here. The other one, we had a plus sign. So first of all, 36 is a perfect square. So I could go ahead and write this as its conjugates because that is the difference of two squares. So then I've got x is equal to 6, x is equal to negative 6. Those are exclusions from the domain. Okay, so if I go ahead and plot, or plot's the wrong word, but put negative 6 and 6 and put circles for each of those numbers, shade around it, that means everything is included in our domain except for those two numbers. And the reason why those two numbers can't be there is if we substitute them in either a negative 6 or a 6, then, and we square them, they'll give us a positive 36, which then creates a 0. All right, so our interval for our domain is going to be negative infinity to negative 6, union negative 6 to 6, union 6 to positive infinity. In set builder notation, our domain is going to be squiggly brackets, okay, the set of all x such that x is a real number and x cannot be equal to negative 6, x cannot be equal to positive 6. Okay, let's do just one more, okay? So for 7, clearly x cannot be equal to 0. All right. And so our interval, we've got right there, an open circle right at 0. And so it would be negative infinity to 0, union 0 to positive infinity. Let's go over to 8. The question is this any different? I mean, it's x raised to the second power. And if I set that equal to 0, the only number that's going to create an issue for us is if x is 0. So that means x cannot be 0. It's going to be the same. This is our exclusion to the domain. So just like the one we just did, our domain is going to be negative infinity to 0, union 0 to positive infinity. In set builder notation, what that would look like is squiggly brackets, x such that x is a real number and x cannot be 0. That's it. Okay. Now, let's start having some fun. Let's try simplifying rational expressions. So when we simplify a rational expression, now we get to play with the numerator, okay? So you're going to factor both the numerator and the denominator, and then you simplify. So that means we use the term cancel, like factors, all right? It's actually more, we're reducing them, but that's okay. All right, so for this first example, all right, if we take our numerator, actually, I'm going to use two different colors here. If we take the numerator, 2x squared plus 5x minus 12, and then it's going to be factored into 2x minus 3x plus 4. The denominator is simply the difference of two squares, x minus 4, x plus 4. So you can see that those two factors are exactly the same. And so they are going to be reduced to 1. So 1 times 2x minus 3 over x minus 4 gives you this 2x minus 3 over x minus 4. That's your simplified rational expression. All right. So let's look at number 9. So number 9 should look a lot like something we've already done. Yeah. Okay. When we were looking at integer exponents, we were doing problems like this. So I'm going to simplify this by drawing a fraction bar. And I'm just going to first look at 6 over 12. And I can think of, whoa, didn't mean to do that. Sorry. I can think of this 12 as 2 times 6. So the 6's reduce, and so I'm left with 1 over 2. Now let's look at our x's. So I've got x, our common base, and then 2 minus 1 is just x to the first. So that x to the first goes in the numerator. Now look at our y's. So that's going to be y to the 5 minus 9, which equals y to the negative 4. Well, that y to the negative 4 would go in the numerator, but that I want that to be a positive 4, so I'm going to put it in the denominator so I can make that exponent positive. Okay, and then lastly, z to the 3 minus 7 is z to the negative 4. So again, that becomes z to the 4th in the denominator. The only thing we could clean up here is we honestly don't need that 1. We can just leave it a plain x up there. Okay, let's go on to problem number 10. So we're going to simplify this. And so the first thing we need to do is we need to factor our numerator. And so that comes with, let's just go ahead, and that you can see for that 10, I'm going to use a 5 and a 2. So that's going to be y minus 5, y plus 2. And then in the denominator, I need to think of two factors that equal a negative 35, but add to 2. So I'm thinking, 7 and 5. So how about if it is y minus 5, y plus 7? That'll work. So then my y minus 5s, they reduce to 1. And so our final answer is y plus 2 over y plus 7. Let's do number 11. So that one, we are going to factor the numerator. I'm going to use 6 and 8. So that's going to be y plus 6, y plus 8. And then in the denominator, this one looks like it is a perfect square trinomial. That first term is a perfect square. Our 64 is a perfect square. So if I take that to a binomial squared, it's going to be y plus 8. So to check that, it'll be 2 times 8 times y, which is 16y. Sure enough, that checks. So now I have a y plus 8 in my numerator, and I actually have 2 y plus 8s in the denominator. So what actually is easier, instead of putting y plus 8 with the exponent of 2, I'm actually going to erase that and put y plus 8 twice. Then I can clearly reduce those to 1. And so I'm left with y plus 6 over y plus 8. Now, let's pause. Many of you are asking yourselves, hey, why isn't she reducing those y's? They're the same. You can only reduce factors. And remember, way back when we were talking about factors, factors are things that are multiplied. The y is not being multiplied times 6. It's being added to 6. Same with the denominator. So those are not factors, so they cannot be reduced. All right, let's look at problem 12. So for problem 12, this one in my numerator, I have got x minus 7, x plus 3. Ooh, and in the denominator, well, that's a little bit interesting. We're going to need to do a little bit of grouping here. Makes it more fun. So we can take out an x squared, so we get an x minus 7. Take out a negative 10, and we get an x minus 7. So now we've got x minus 7, and then an x squared minus 10. So my x minus 7's reduce, and I'm left with x plus 3 over x squared minus 10. That's as good as it gets. That x squared minus 10 is not a difference of two squares. 10 is not a perfect square. Yes, I know that 5 plus 5 gives me 10, but that's not how perfect squares work. It would need to be 5 times 5, which would actually be 25. All right, let's look at 13. 13 is a good one. I love 13. So in the numerator, we've got this m plus 1. In the denominator, we have the sum of two cubes. Our a is m, our b is 1. So that's going to be m plus 1 times m squared minus 1 times m is m plus 1 squared is 1. All right, so my m plus 1's reduce, but they reduce to 1. So there's a 1 left there. So my final answer is not m squared minus m plus 1. It's 1 over m squared minus m plus 1. A very different animal. All right, now let's look at simplifying ratios of -1. We were introduced to this idea a little bit earlier, and it's back. It is back. So this, when you have a subtraction problem, you can flip the A and the B, or change positions with the A and the B, as long as you factor out a -1. Okay? All right. So, if you have, let's kind of play with this a little bit. If you have A minus B over a B minus A. Okay. So let's make this a little smaller. Let's take that numerator. No, let's take the numerator and leave it alone, A minus B. Let's take the denominator. And if we want to change the positions of that A and B in the denominator, we can do that by taking out a -1, and then we've got the A minus B. Why would we want to do that? Well, because then the a and the b reduce, and this is equal to a negative 1. All right, well, that's like a lot of work, a lot of thinking. Is there a shortcut? Yeah. Okay, so look at this. If you notice that your a's, like one of your terms, opposite signs. My a on the top is positive, the a on the bottom is negative. Now, let's look on the other way. The b's. The top is negative, the bottom is positive. Okay? So they're both opposite. Every time that happens, it is equal to negative 1. Okay, so let's see how that might work. So we've got this 5 minus n over n squared minus 25. So in the denominator, that's the difference of 2 squares. And so that means we could put it in its conjugate. N minus 5, n plus 5. Now let's just look at these subtractions. We got the n minus 5. In the numerator, it's 5 minus n. So they are opposite signs. The 5s are opposite signs. The n's are opposite signs. So I can reduce both of those, and that's equal to a negative 1. So then my answer is negative 1 over n plus 5. You can put this negative out front, or if you're more comfortable keeping it in your numerator, you could do that. Same thing. And Connect Math will recognize them as being the same thing. All right, let's look at number 14. So we first need to factor the numerator. So 6s are always fun, okay? So we're looking at what can we multiply that gives us negative 6 but adds to positive 1. So we're thinking of 2s and 3s. So if we're looking at multiply to give me negative 6, add to a positive 1. If we're looking at a 2 and a 3, we'll make the 2 negative, okay? So that's going to be x minus 2, x plus 3. There we go. In the denominator, see how my x squared is right over here? It's furthest to the right. Okay, well, we're going to leave it there. When we are factoring, our x is going to be on the right in each binomial instead of the left. So I'm looking for what can I multiply that gives me 14 but adds to a negative 5? Okay, so I'm thinking negative 2, positive 2, negative 7. Okay. So it's actually this negative goes with that 14. It's a negative 14 and a negative 5. There we go. All right. So this is going to be, it's going to be x 2 plus x, what am I messing up? Yes. 2 plus x, 2 minus x. It's going, because we've got the negative here, 2 minus x, and we've got then 7 plus x, okay? So these two, x minus 2 and 2 minus x, they're equal to negative 1. And so we end up with negative x plus 3 over, over 7 plus x. There we go. Now that one was kind of tricky one. You know, even I had to pause. So another way you could have looked at this denominator, I'm going to show you, is, and let's do it in blue, okay? So you could have rewritten it as negative x squared minus 5x plus 14. We don't like that leading coefficient to be negative, so we take out the negative as a greatest common factor, so that'd be x squared plus 5x minus 14. There we go. And then when we factor that beauty, we get a negative on the outside, and it's going to be x plus 7, x minus 2. So you could see where if you had that, it would be in the numerator, x minus 2, x plus 3, and in the denominator, you'd have a negative, I'm going to put the x minus 2, and then the x plus 7. So the x minus 2's, so your final answer would be this x plus 3 over x plus 7, and then you've got this negative that we can just put outside of that rational expression. All right, let's look at example number 15. So I have a 2 minus x in the numerator. In the denominator, I have the difference of 2 cubes. So my a is x, my b is 2. So that is going to be x minus 2 times x squared plus 2x plus 4. So my 2 minus x in the numerator and the x minus 2 reduce to negative 1. So my final reduced rational expression is negative 1 over x squared plus 2x plus 4. Last example. I'm going to take out a greatest common factor of 2 from the numerator, and we get 2 times x minus 10. In the denominator, we have 10 minus x. These two reduce to negative 1, so then my reduced rational expression is negative 2. Now you're ready to complete the homework for 5.1.